So, welcome to the next chapter in the Deep Learning by Aaron Goodfellow series. This series is based on the book Deep Learning by Aaron Goodfellow, Yoshua Bengio, and Aaron Courville. This is the next chapter in the series, Deep Feedforward Networks, and let's just get right into it. So, what exactly is a deep feedforward network? So, this is what. So, the first term was called the first time this idea was introduced, it was called basically a multi-layer perceptron. I might have introduced this in the previous videos. It was a pretty basic one, and it was actually introduced in 1950s. So let's just define what a deep feed-forward network or a feed-forward neural network, or just basically a deep network is defined as. So basically, this defines a mapping called like y equals f x is to theta, where x is input and theta is the parameters. And this mapping is supposed to learn the parameters in order to best represent the data that is input. So, formally, the definition again: a feed-forward network defines a mapping y equals f x theta and learns the value of the parameters theta that result in the best function approximation. So basically, we're trying to approximate this function f x, and which is find the best function approximation, or basically the best representation learning. Now, deep learning was, of course, like first introduced by. I mean, this only became relevant after Jeffrey Hinton, the godfather of AI, made it popular. Before this, any kind of learning was just impossible, or the entire area of AI and machine learning are part of the much larger field called representation learning. We just try to represent the world, and it was simply not possible in any of the previous models, and it was only possible first using deep learning. And this is why this is revolutionary. And so, uh, just for an example, this is like an example neural network, deep feedforward network, and now this would be called as an input layer. This set of layers here would be called as hidden layers. Now we only have one hidden layer here, which has many neurons in it. This would be called as a output layer. So this is the hidden layer. This is the output layer. This would be the input layer. Uh, that is just an example of it, and so basically, how did this even evolve again? The one way to understand these feed-forward networks is to just begin with linear models and consider how to overcome their limitations. Now, the linear models, which we saw in the previous chapters, such as logistic regression and linear regression, are appealing because they may be fit efficiently and reliably, either in closed form or with convex optimization, but they're pretty inefficient. Uh, they have this obvious defect that the model capacity is limited to linear functions. The model just cannot learn anything that's non-linear. So how to extend these linear models to represent non-linear functions of x? So that's what we were seeing here, to the x that we're seeing here. So how to make it, how to make them learn something that's non-linear. So, basically, you can say a kind of introduction. And how do we exactly go about making them? So one way would be to use radial basis functions. So how to make how to basically extend models to represent non-linear functions. How are you going to do that? So one idea would be to using RBF, which is a radial basis function, also known as a Gaussian kernel. So here we just use like a very generic pi uh, with generic nonlinear transformation like phi that is implicitly used by the kernel machines based on the RBF kernel. If phi of x is of high enough dimension, we can always have enough capacity to fit the training set. But generalization to the test set often remains poor. Very generic feature mappings are usually based only on principle of local smoothness and do not encode enough prior information to solve advanced problems. So I mean, this is basically not that efficient. So if I were to draw how this looks like, let's say we have all the data here, data points. So this is kind of the Gaussian kernel, also called as the radian basis function. So this whole set of idea is one way to do it. Or otherwise, let me just see. Nice. So second one would be to use just like manual engineering, and this is kind of dumb. And you just manually engineer this phi, which is the nonlinear transformation, and so this was basically the dominant approach until we figured out how to do deep forward neural networks. And this requires a lot of human effort, just not scalable. So if you look at the third way, this is to use the damn deep forward feed-forward networks. So this is highly scalable. Here we can learn a lot of data, and this is just the way. And this entire chapter, this is what we'll be learning. And so to get started, let's just use an example. If we just take so I'm just trying to use this color, which is basically color of the textbook. So let's take an example of learning XOR. Okay. We all know what a XOR function is. Hopefully, it is just like an AND. So it is a slight modification of the OR operator. And so how do we learn this XOR function? So we can basically treat this problem as a regression problem and is a mean square error loss function. Let me just define what it looks like. The input, we have 0 0 transpose 0 1 transpose 0 1 1. These are all the possible combinations, and the that would be the input. So, and we are taking on the whole training set. The let's define the cost function with j. So this is sorry, this is a loss function as x, and we minus the target function uh, from the model function. So this is the model function, and we are subtracting this from the target function. So target function, and we choose the form of a model, which is this. This is our model. Remember, so our model that we're trying to create. This is the target function. And for solving normal equations, we obtain tool equals 0 and b equals 1 by 2. Okay, that was okay. So let me define the model. So f x w p x transpose w plus p. And b is bias, x is input, and w is the weights. So now let's introduce a very simple feedforward network with the one hidden layer containing two hidden units. And let's try to present this. This is another scene. It's basically chapter 1. So we have this is x1, x2, h1, h2. This is y. It's a very simple feedforward neural network. And let's represent this as so this is their equivalent, by the way. So just to make it easy to read and represent, we will compress the layers. So basically in this style, the matrix W describes the mapping from X to H, and a vector small w. This is a vector because there's only one dimensions. There's only columns in it. There is no rows. Or there are rows and no columns. So the vector is we discover vector. We discuss the mapping from H, the hidden layer, to the output layer Y. This is kind of a compact description, and let's define. So the output layer is still just a linear regression model, but now it's applied to H rather than to X. The network now contains two functions chained together. So two functions are H equals if one means the layer WC, and Y equals F2 HWP, with the complete model being just F X WC WP equals F2 F1 X. It's kind of the overall representation. Now, what function should F1 compute? So the linear models have served us well so far, and it may be tempting to make F1 linear as well, but F1 If it were linear, then the Feedforward network as a whole would remain a linear function of the input. Ignoring the intercept terms for the moment, suppose f1 equals like wx and f2 of h equals hw, then f of x would be equal to small w into large capital W times x, and we then represent the function as f x equals x transpose times small w dash. Clearly, we won't take that approach. We must use a nonlinear function to describe the features. So most linear networks do so by using an affine transformation controlled by learned parameters, followed by a fixed nonlinear function called an activation function. We use that strategy here by defining h equals g w. This is the uh, mapping from the input layer to the hidden layer we saw. This is the input. So this is the bias. So this W here provides the weights of a linear transformation, and C provides the biases, as I said. And previously, to describe the linear regression model, we used a vector of weights and a scalar bias parameter to describe an affine transformation from an input vector to an output scalar. Now we describe an affine transformation from a vector x to vector h. So an entire vector of bias parameters is needed. So the activation function g is typically chosen to be a function that is applied element-wise with the hi equals, if I were to put I here, so it will become like a g of x uh, transpose times w plus ci. Model neural networks, the default recommendation is to use ReLU, a rectified linear unit, and defined by the activation function. So ReLU, as we will see later, it's the activation function can be defined like this. Okay. And the ReLU basically, if you were to draw a graph of ReLU, it basically looks like this. Anything before the 0, the output would be just 0. Anything above 0, the output would be the same as the input. So we can now finally complete our neural network like this. If x, this is input, this is first layer, and this is its bias, the second layer, and then its bias, and this is the transformation of the second layer. And since we're applying a thing on that, you take a ReLU from the first layer, a transpose of it, with bias on the first layer, plus b. Yeah, this in other words, this is basically like f transpose of like the first layer. Basically, we are applying a ReLU. Let's say, I mean, this is the informal representation from the first layer. So f1, so f2 would be like this. So we are applying this function on top of the first layer function. This is the function for the second layer. And now the textbook goes on with the actual numbers, and we will just skip that. As you know, I mean, just in case if you guys did not know, this entire series is called Skim series. So basically, I was skipping a lot of details. This is just me learning everything, uh, and I'm not a professor or anything. This is this is all new to me as well, and I've just gone through this explanation. Turns out to be the best way to learn it, and that's exactly why I'm doing this video series. I don't expect anybody to watch this, nonetheless. Uh, I may make a better series later, and this may also be turn out to be useful. But I'm really not uh, focusing on how best to be useful, not right now at least. So if you rename it, this basically scene 0, and this would be scene 1 or chapter 1 if you will. And let's go to gradient based learning. So let's go to this second one. Uh, so whatever color we had used. So the second main section in this chapter is gradient based learning. Okay, let's try to pick up the speed a little bit. During designing and training a neural network is not much different from training any other machine learning model with gradient descent. And as we saw, I mean, the just gradient descent and stochastic gradient descent have their differences. I might make another series on the machine learning basics again, but we just not focus on that right now. So the try to get the actual difference between the stochastic gradient descent. Yeah, so stochastic gradient descent updates parameters after each individual data points. So it's faster and scalable, and it may be noisy, and its convergences may be like oscillating. It doesn't convert smoothly. Just plain gradient descent converges smoothly, but it's late. It's not scalable. It takes full data to compute gradient parameters. So stochastic is just a better option, although it's a little bit more noisy than just plain vanilla gradient descent. Now, why that topic came in the first place? Well, here we'll be talking about gradient-based learning, so it's not much different from gradient this one. And the largest difference between linear models we have seen so far and the neural networks is that the non-linearity of a neural network causes the most interesting loss functions to become non-convex. What exactly is a non-convex function? Let's see, non-convex function. So a non-convex function is the one that curves up and down like a ball-shaped convex function. Convex is just simple like this. So non-convex would be like that. And yeah. So unlike nonlinear, here we may see non-convex function. The specific algorithms are implements and refinements to the ideas of gradient descent introduced in the earlier section. So here we will discuss about several techniques in gradient-based learning. Now, you can of course train models such as linear regression and support vector machines with gradient descent too, and in fact it's common in training set is extremely large. From this point of view, training a neural network is not much different from training any other model. As with other machine learning models, to apply gradient descent, we must first choose a cost function, and then we must choose how to represent the output of the model. And So the first section in here will be cost functions. So what exactly is a cost function? Cost function just tells you the difference between your model and the actual value in the dataset. So what your model predicted minus what the actual uh, data is. So value in the data is basically it lets you choose. Uh, it lets you tell what is the cost of your model. So the higher the cost, the worse your model is. Your goal is to bring the cost of your model as less as possible. And so inside the cost functions, there is some more topics. So let's learn about what is a learning conditional distributions. So learning conditional distributions with maximum maximus decimus meridius. Oh, that's the gladiator guy, Russell Crowe. So with the maximum log likelihood, basically, let's see what this section says. Most modern neural networks are trained using maximum likelihood. This means the cost function is simply the negative log likelihood. So the cost function is cost function of theta, the parameters, is just a negative log likelihood. And this means so equivalently described as the cross entropy between the training data and the model distribution. Like I said, the actual data and what your model has predicted. So we'll take the cross entropy. Why cross entropy? Because this is the better way to get the difference. The data. So the cross entropy, negative log likelihood of the model of your model y per x. So this is basically it. A specific form of cost function changes from model to model depending on the specific form of log p model. The expansion of the above equation typically used on the terms that do not depend on the model parameters may be discarded. For example, as we saw in the older section, if p model y bar x equals n y f of x and I, then we recover the mean square error cost. And so basically, we could turn this into we can discard the log and convert it to another way. But one must note that for real valued output variables, if the model can control the density of the output distribution, for example, by learning the variance of parameter of a Gaussian output distribution, then it becomes possible to assign extremely high density to the correct training set outputs, resulting in cross entropy approaching negative infinity. Regularization techniques described in chapter 7, the later chapter, provide several different ways of modifying the learning problem so that the model cannot reap unlimited rewards this way. So there's a catch going on here. So we don't want that catch to catch up with us. So now going to the next one, learning conditional statistics. Instead of learning a full probability distribution p y bar x, we often want to learn just one conditional statistic of y given x. For example, we may have a particular f of x. We wish to predict the mean of y. So if if we use a sufficiently powerful neural network, we can think of a neural network as being able to represent any function f from a wide class of functions. And We can view the cost function as being a functional rather than being just a function. A function is mapping from the functions to a functional. What is functional? A functional is a mapping from functions to real numbers. Functions to real numbers. Solving an optimization problem with respect to a function requires mathematical tool called calculus of variations. It's not necessary to know the calculus of variations exactly, but it is necessary to understand the calculus of variations may be used to derive the following two results, which are one first result derived using calculus of variations that solving optimization problem, such as f of star whenever we say star, it's basically our function arg min of f cross entropy x y of p theta y minus f of x all squared. So this is still the cost function. This is we're just using conditional statistics. Well, if you were to first result derived using calculus of variations is that solving this optimization problem will give you f star of x equals expectation of y only y of p theta of y. So long as this function lies within the class we optimize over, basically, if sorry, if we could train an on infinitely many example samples from true data generation distribution, meaning the mean square error cost function gives a function that predicts the mean of y for each value of x. Different cost functions give different statistics. A second result derived using calculus of variations is it kind of looks similar to this. Unfortunately, mean square error and mean absolute error often lead to poor results. Basically, mean squared error and mean absolute error, they give poor results. We don't want to be using them. Some output units that saturate very small gradients when combined with these cost functions. And this is one reason that the cost center free cost function is more popular than mean square error or the mean absolute error, even when it's not necessary to estimate an entire distribution of p of x. So even though in conditional statistics we are using this conditional and instead of the entire thing, turns out this is just better. So this is kind of a arrow mark. So yeah, so this is bad. This is better. So cross entropy. This is a cross entropy, as you can see. The is turns out to be better than the conditional entropy. Now coming to the second one here. So we just talked about cross functions. Let's talk about output units. Output units. And the choice of cost function is tightly coupled with the choice of output unit. Most of the time, we simply just use cross entropy between the data distribution and the model distribution. The choice of how represented are the output then determines the form of the cost entropy function. Any kind of neural network that unit that may be used as an output can also be used as a hidden unit. Just kind of interval. So any neural network unit that may be used as an output unit can be used as a hidden unit. So basically, in hidden unit, one unit is just outputting its thing to another hidden unit. So this is why this makes sense. And let's go through some of the linear units that can be used. So let's just say we have 1, the linear units for Gaussian output distributions. Gaussian output distributions. And this is linear output layers are often designed to produce the mean of a conditional Gaussian distribution. Maximizing the log likelihood is then equivalent to minimizing the mean square error. So the equation we can write here would be like this. It's just and this y, where again I is the parameter, y is the y is what forms the function for n, and so maximizing the log likelihood is equivalent to minimizing mean square error. Because linear units do not saturate, they pose difficulty for gradient-based optimization algorithms and may be used with a wide variety of optimization algorithms. So let's move to the next one, which is sigmoid units. We use sigmoid itself units for Bernoulli. Again, Gaussian is basically like uh, it's like it's a smooth like if we were to say like Gaussian distribution looks smooth. Okay, so Bernoulli distribution output distribution. Bernoulli looks binary, obviously. Like it is binary. And well, what does sigma units do? Basically, the maximum log likelihood approach is to define a Bernoulli distribution or y condition on x. A Bernoulli distribution is defined by just a single number. The neural net needs to predict only py equals 1. Basically, you only need to get like py equals 1 given x. That's what this is. Maximum log and name of by weights and biases. So this would need to define a valid conditional distribution, but we would not be able to train it very effectively with gradient descent. It has some problems with it, which is why enter sigmoid units. A sigmoid unit is defined by okay, sorry, that's not sigmoid. It would be sigmoid. So y hat equals sigmoid transpose h plus p. Now, the sigma is the logistic sigmoid distribution function, which we saw in previous chapter, and so the loss function for a maximum likelihood learning of a Bernoulli parameterized by a sigmoid is negative log likelihood of p of y given x, which can be written as sigmoid. This is the sigmoid Greek letter 1 minus 2y c. Okay, let me title. Okay, it's not curvy enough. Yeah. So this is the sigmoid. So well, the bottom one is when we use other loss functions such as mean squared error, the loss can saturate anytime the sigma saturates. Sigmoid activation function saturates to 0 when z becomes very negative and saturates to 1 when z becomes very positive. The sigmoid, just in case anybody is not aware, sigmoid function is what it looks like. So and turns out it's not that great. So max log likelihood turns out to be better than this sigma shit, sigma stuff. And let's go to the next one here. Softmax units. Softmax units for multi-nully output distributions. Multi-nully is again just an array. Like binary, it's an array. And anytime we wish to represent the probability distribution over a discrete variable with n possible values, we may use the softmax function, but it can be seen as a generalization of a sigmoid function which was used to represent a probability distribution over just a binary variable. So we don't want that. We want something better than that, which is softmax. Softmax is kind of like argmax, but it's better. No, argmax, if you guys know, just maximizes the argument. So let's still get argmax. This is what it will look like. Basically, the value that the the input value for which the output is the highest, that input value is the your argmax. So whatever makes this f of x maximum, and that input value is the value of the argmax of f of x. Argmax is different for functions. Softmax basically argmax softened. So don't confuse softmax with the fact that it's named like a maximum function. No, it's more of a softer argmax, so softened argmax. And it will describe the well, there's something interesting here as well, something about neuroscience. So let's see that here. From a neuroscientific point of view, it is interesting to think of a softmax as a way to create a form of competition between the units that participate in it. Now, the softmax output always sum to 1, so it's kind of a like zero-sum game. So an increase in the value of one unit necessarily corresponds to a decrease in the value of other units. This is analogous to how the lateral inhibition that is believed to exist between nearby neurons in the cortex. So it's kind of like a so kind of like a lateral inhibition in neural cortex of the brain. As the extreme, when the difference between the maximal A and the others being large magnitude, it becomes a form of winner take all situation. Basically, it's zero sum game. And yeah, that's about it. Now there are some other output types as well for other output unit types, which can also be used in hidden layers as we saw. And we will just skip this. Well, regardless of whether we use a standard deviation, variance, or precision, we must ensure that the covariance matrix, the Gaussian, is positive definite. And well, there's also this concept of mixture density networks, where you use neural networks with Gaussian mixtures as their output. And there's mixture components, there's mean covariances, there's a concept of clipping gradients when there's some errors, when the gradients is causing some errors. And the neural network is able to learn nonlinear mappings from the input to the parameters of the output distribution. These parameters include probabilities governing which the mixture of components for example. Yeah, so we'll skip those parts. Basically, just know that there are some other output unit types using similar concepts. And well, this was scene 2, let's say. And yeah, so let's go to scene 3, just hidden units. And basically, this is what we see in the mid of the neural network. And rectified linear units are an excellent default choice for hidden units. Let's just say that rectified linear units, kind of like the default choice of hidden units. Many other types of hidden units are available. It can be difficult to determine whether to use which kind. We describe here some of the basic intuitions motivating each type of hidden units. It's usually impossible to predict in advance which will work the best. You kind of do experimentation here, so there's no free lunch theorem as we have seen. So you have to go and discuss, go and experiment, find out, and you have to do FAFO. And the rectified linear function g of z is equal to max 0 z is not differentiable at z equals 0. Basically, if you take this thing rectified, this value defined like this, its graph would look like this. Graph like this. The value would have it here and here. So basically, it's not differentiable here. Then how the hell are we using it in gradient descent? How the hell are we using it as a hidden unit? But basically, the thing is, in in practice, we don't actually get to 0 in gradient descent. We may get closer to 0, but almost never 0. And this problem, the fact that even though not differentiable at x equals 0, value is just fine for most tasks, as gradient descent almost never reaches 0. Okay, hidden units that are not differentiable, usually non-differentiable, are only a small number of points and all that. So you can safely disregard this non-differentiability of hidden units. Activation functions are described below. And now there are some generalizations of rectified linear unit. We'll just go through a few of them here. So some generalizations. Generalizations. Well, there are quite some of them. So there is also as a result there is a ReLU that we just saw. Now there is also other kinds of ReLU. We'll see here. We just draw the graph, the rough graph for them. So you saw this is ReLU. There is also leaky ReLU, also ReLU, and there is there's a swish, there is Gaussian, there is randomized ReLU, there's absolute value ReLU, and there's just it's like randomized ReLU, swish ReLU. So there's lots and lots of those types. This is standard ReLU again. Should be leaky ReLU. This is the ELU, just exponential unit, linear unit, exponential linear unit, and scalar exponential linear unit. Okay, we won't go to that. This would be the absolute value. This would be randomized leaky value. So it's kind of like a RR value, R value, and there is a swish value, and there's some more of them. Basically, the generalizations of rectified linear units are based on using just a non-zero slope, and like the absolute value rectification is one of them. A leaky value, a parametric value, or a prevalue. That was parametric value. Okay. Parametric value. These are again approximated diagrams. Now, there's a thing called like catastrophic forgetting, and so what the hell is the catastrophic forgetting? Let's go through that a bit. Okay, let me just select some things here. Yeah. So now, if we were to go to this special, let me, yeah. So what is what was we talking about? So what is a catastrophic forgetting? This is a special topic again. So catastrophic forgetting happens when your model just after learning a lot just tries to forget everything. This is a topic even discussed today as well. This is not like some old topic. So and th- this happens when your model tries to fail to strike a balance between stability and plasticity. So stability is your model's ability to have a good grasp and stability on what it has learned. Plasticity is the model's ability to learn new concepts. Now your model just when your model becomes a little too plastic, it just loses all its previous learnings. That's when the catastrophic forgetting happens. And it's a sad situation. It is still one of problems, and there are some mitigation algorithms, techniques that is being used, uh, like the deep learning, the DeepSeek guys from China. They invented a technique uh, called like mixture of experts technique and such. So there and the research is still going on, and this is one thing to just take care of. So moving on, the ReLU and all the generations of them are based on the principle that models are easier to optimize if their behavior is closer to linear. Again, the main principle, as I've iterated many times in the deep learning, is that instead of inventing complex algorithms, it's much better to uh, have ideas or algorithms that are simple but easier to build upon and optimize. So which is why I mean the transformers have this linearity and hence it's easier to just parallelize and optimize them. And rarely you have this linearity as well. Uh, so instead of something that's way too complex and only applicable for one thing, you build one small thing that is highly scalable and easier to optimize. And max out generalizes ReLU and leaky ReLU by taking maximum of a set of linear functions, creating a piecewise linear approximation. Okay, so the next concept here is point two, logistic sigmoid and hyperbolic tangent. Logistic sigmoid and hyperbolic tangent. What was exactly? The widespread saturation of sigmoidal units can make gradient-based learning kind of difficult, which is why we use their use as hidden unit in feedforward networks is now discouraged. Well, that's kind of a sad thing, isn't it? Sigmoid units are just not used. Well, that's what we're studying here. So, but when sigmoidal actuation function must be used, the hyperbolic tangent actuation function typically performs better than logistic sigmoid. It's, I mean, so basically, really simply better, much better than whatever this is. So sigmoid, because of the white space saturation, making the because make JD difficult to perform. Now this is used in recurrent neural networks, but who uses recurrent neural networks anyway? So still useful for recurrent neural networks, a topic that we will discuss later. But transformers have overtaken what R and N were supposed to do today. So we just want to use them. There's basically no you need to use these things. They also book also discusses about some other hidden units like radial basis function, third hidden units, which example, like radial basis function. There is also soft plus max, hard tan hedge, and they are reasonable, but the research is still under process. They're not that widespread as rarely is. So that's about that. That completes the third smaller unit of this thing, and this whole chapter. So now let's get to okay. It's refusing to go down. Okay, so what about the architecture design? How do you go on designing about these things? Yeah. So again, you need to just mix and match, and there are some theories here. Like the free lunch theorem goes, there's no overall. There's not like one thing is just better for a lot of things. It's just not the case. So let's go through universal approximation properties and depth. Uh, Universal approximation theorem by Hornick et al. And Semenko in 1989, literally, states that a feed-forward network with the linear output as the logistic sigmoid activation function. Okay, sorry. So again, to reiterate, universal approximation theorem states that a feed-forward network with the linear output layer and at least one hidden layer with any squashing activation function, such as logistic sigmoid activation function, can approximate any Borel measurable function from one finite dimensional space to another with any desired non-zero amount of error, provided that the network is given enough hidden units. The derivatives of feed for a network can also approximate the derivatives of the function arbitrarily well. The concept of Borel measurability is beyond the concept, beyond the scope of this session. So basically, it says that if you can just squash, if a function is like a Borel measurable, Borel 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 measurable, then it can be uh, represented by an MLB. But there is some catch here. So now this says that basically what this guarantees is that it says that MLP can says MLP can represent, you know, the representation learning is the whole idea of this entire deep learning. It says MLP will be able to represent this function, this data, whatever we have. It doesn't guarantee, but not no guarantee uh, that the training algorithm can learn it. So even if the MLP is able to represent the function, learning can fail for many reasons. First reason it can fail is that optimization algorithm used for training may not be able to find the value of the parameters that correspond to the desired function. Second, recall from the older section, if you remember, no freelance theorem that I have been saying quite a lot. There's no one thing that can do everything. So there's no freelance. So all it guarantees that your MLP can represent it. Doesn't guarantee your algorithm can learn it, be able to learn it. So it's kind of like a Turing machine, I think, on a very high level. It's kind of like that. So this says that there exists a neural network large enough to achieve any degree of accuracy we desire, but the theorem itself doesn't say how this large this network will be. So how useful is that? Well, not much useful is it? Well, the concept themselves are useful. Now, there's another concept called folding by Montufar et al. Um, such as a deep network can reuse and combine folds to build complex decision boundaries, and the fact that shallow network need more neurons. So basically, this is by Montufar et al. 2014. So what they did is, so let's say you have like data like this. You need to fold on these pages. Then it becomes like this, doesn't it? So it becomes like this. And then you fold again. And then becomes even more folded. So it's best to look it up. So this is how the Montefiore they have come with an idea that you'll be able to like they showed that the piecewise linear networks which can be obtained from rectified non-linearities or magnitude units. These piecewise linear networks can represent functions with the number of regions that is exponential in the depth of the networks. So even if the data is exponential, they can present in this way. This is not that big yet. This is not like widely used today, but it's a very good concept to consider. Again, there's no guarantee that the kinds of functions we want to learn in applications of machine learning share such a property. They must share the property of this like mirroring thing. If you cannot have this particular property, your algorithm just cannot learn. Uh, what what are some other architectural considerations? Other architectural considerations. What are they? Well, many neural network architectures have been developed for specific tasks. Specialized architecture for computer vision called convolutional neural networks are, well, we'll see that later. Feedforward neural networks may also be generalized to recurrent neural networks for sequence processing. So we, we have quite the number of architectures as we know. So there is convolutional neural networks, there is neural networks, there are transformers, not yet famous as of the time when this book was written, but as I know, as I happen to know, transformers are a big architecture. So transformers use the attention mechanism again. So they use attention and MLP. Now attention is used 33%, and standard multi-layer perceptron is used like 60% of the times. And there is remember that the backprop that we'll see in the next section is used in training 100% of the times, not in inference. So when you ask a LLM question, it's not backpropagation that is being used, but the grace of transformers. So one important takeaway that we'll have here is that deeper models just seem to perform better. You know, deeper models tend to perform better. This is not merely because the model is larger. This experiment from Goodfellow, Aaron Goodfellow, the author of this book, shows that increasing number of parameters in layers of convolutional neural networks without increasing the depth, just increasing parameters, is not nearly as effective as increasing the test set performance. At increasing the test set performance, the legend indicates the depth of neural network used to make each curve and whether the curve represents the variation in the size of the convolutional or the fully connected layers. Yeah, so basically we observe that the shallow models kind of overfit at around 20 million parameters, and a deep model expresses a useful preference over the space function stuff that model can learn. Specifically, it expresses the belief that functions should consist of many simpler functions composed together. This could result in either learning a representation that is composed in terms of simple representations, example corners defined in terms of edges, or in learning a program with sequentially dependent steps. Example, first look at stiff objects and then try to segment them from each other and then recognize them. So basically, deeper models are better. This is exactly why there's so much competition over the GPT-2 was just like 124 million parameter model, and the better models as of today are just larger models than what you see previously. So if you see like Gemini 3.0 or like Grok 4.1 or GPT 5.2, they are just larger than their previous versions. So that is one big deal. And well, that completes like half of the main concepts of this chapter. In the next section, we will in the next chapter we will see about backpropagation. So that's about it. Backpropagation is a big topic, and this video is already very long, so it's just better to break it here.